Hello everyone, my name is Poonam Deshpande and today's lecture is about method of variation of parameters to find particular integral of higher order LD, which is a sub part of the solution. Uh, Now we already know how to find a particular integral, that is YP, depending upon the types of f of d and the function capital X, which is always to the RHS of the higher order LD. So let us first know what is method of variation. Okay, so before we start, to know what is the method of variation of parameters, the question is, why do we use this method? So whenever we have already seen some traditional methods, I've given you some standard functions, their corresponding YP is already given. But sometimes these methods fail to solve the given higher order LD, and in those cases we use the method of variation of parameters. But that means that suppose if you come across functions like sec x, tan x, or e raised to x into tan x, or cosec x, which are not given in the list of standard functions, or you come across a differential equation of this type, where you can see RHS is not of the any of the function which you have already seen. So in this case, we use the method of variation of parameters. Now let us understand what exactly the method is. Okay, so before we understand the method, let me remind you that this method is applicable for any order of the higher order linear differential equation. But for simplicity, we are going to start with the second order linear differential equation, which is given by this equation. Okay. Now this x is that function that I mentioned earlier, which is to the RHS of the second order LD. You can see this is the LD with the constant coefficients. So what we do is, as usual, we will solve this given differential equation for finding the complementary function, and we can write that complementary function in a special form, and that particular for special form is c1 times some function y1 plus c2 times some function y2. So y1 and y2 can be maybe e raised to ax or sin x, cos x, some of the standard functions. And then once we have the expression for yc, then we can assume that yp may be written as this equation, particular equation, that is u times y1 plus v times y2. Here y1 and y2 are already known from the previous step, and now our task is to find the value of u and the value of v, which are unknown. So how do we find that? And for that we have formulas given. So u is given by the formula minus of integral y2 times x upon w dx, and v is given by integral y1 into capital X upon w dx. Now capital X is this function which is to the RHS of the given LD, and what is w? The capital W is nothing but called as a Wronskian, and it is defined as or given as this. So W is equal to determinant of the two functions which we have calculated in YC, that is y1, y2, with their respective derivatives. Okay, once we know this method, I'm going to give you an algorithm for finding the solution using the method of variation. Although I have already explained what are the steps, but let us just go through the algorithm to understand what steps we follow to solve higher order or second order LD using method of variation of parameters. So step 1 is to find the complementary function and write it in this form so that you get y1 and y2. Step 2, we write what is value of y1, what is value of y2. Step 3, we assume yp as u times y1 plus v times y2, where y1 and y2 are from step 2. Step 4, first we calculate the Wronskian, which is given by this determinant, and then we calculate u by the given formula that I've already given you. Once you get the values of u and v, we substitute back in this yp equation, and then we get our required solution, that is yp. Now just like the second order LD, we can also use this method, the method of variation of parameters, for solving the third order linear differential equations. Let us look at that. Okay, let us consider a third order LD with constant coefficients given by this particular equation. Just like the previous method, we are also going to find the complementary function for this higher order linear differential equation, and it will be written as this: yc equal to c1 times y1 plus c2 times y2 plus c3 times y3. So the extra thing is this new variable y3 and this constant c3. Then again we assume yp to be this particular expression, that is u times y1 plus v times y2 plus omega times y3. So the what is the difference between this and the previous method? Here we have one extra variable, that is y3. So let us look at what are the values of the unknowns u, v and omega, and they are given by these formulas. And you can see that since that u is the first unknown here, we skip y1 and we consider y2 and y3 to calculate u, that is y2 times y3 dash minus y3 times y2 dash etc. times x upon w dx. So in a similar way, you can see that v, when you calculate v, we skip y2 and we consider y3 and y1 in that order. Okay, so we skip y2, then we consider y3 and then y1. Therefore, we have y3 into y1 dash minus y1 into y3 dash times x upon w dx. And omega, can you guess what can be omega? Yes, omega, we need to skip y3 and then we go in the order of y1 to y2. So y1 into y2 dash minus y2 into y1 dash times x upon w dx. Now here this Wronskian is a 3 cross 3 determinant, unlike the previous method, that is 2 cross 2. So let us see what is the definition of this Wronskian. It is defined as the 3 cross 3 determinant, where first row is this functions y1, y2, y3, second row is their first derivative, and third row is their second derivatives. I'm sorry, I've missed one dash here. This is actually y1 double dash. Okay, so with this we end our lecture, and then the examples will be solved in the successive lectures. So this is part 1 of this method of variation of parameters lecture, and in part 2 we will see how do we solve examples based on that. Okay, that's it for today. Bye.